SwayamPrabha. Digital India. Educated India.
So, what do we get from this lemma? So, what we can say is the following now, that if C is a monotone circuit for click and C is identically 0, then size of C is at least n choose k by m square into n minus L minus 1 by k minus L minus 1. Okay. So, this is not very difficult to see. So, this is just combining what we saw. So, okay, let me remove this proof. So, firstly, so what kind of approximator are we looking? So, we are saying that if the approximator for C is identically 0, right. So, what does it mean to say an approximator is identically 0? So, a 0 approximator fails for what kind of graphs? So, what kind of graphs should it output? 1. It should output 1 if the graph has a click, right. So, basically that means it is failing for all positive test graphs. So, a 0 approximator fails for all positive tests, right, all positive test graphs. Therefore, well, and what do we have from lemma 2? From lemma 2, the number of positive tests on which a gate fails is at most m square into n minus L minus 1 k minus L minus 1, right. So, the number of positive tests which fail on some gate will be size of the circuit times this, right. So, basically at most I mean it is an OR over all these things. So, therefore, number of positive tests that fail is at most, we know that OR gates anyway do not fail, but suppose the circuit had all AND gates, okay. So, it would be size of C times m square times n minus L minus 1 by k minus L minus 1, okay. So, the number of positive tests that fail is at most this, and by this the number of positive tests that fail is at least the total number of positive tests, which is n choose k, right. So, combining, what do we get? N choose k is at most size of C times n square into n minus L minus 1 times k minus L minus 1. Therefore, size of C is greater than or equal to n choose k by m square into n minus L minus 1 times k minus L minus 1, right. Okay, so this completes the proof of lemma 3. Now, if you look at the proof of this lemma, actually this is saying a little more. What is it saying? It is not just talking, it is not talking about the size, it is talking about what kind of gates. What kind of gates is it talking about? It is talking about AND gates over here, right, because OR gates do not fail. So, what it is saying is that the number of AND gates in C is at least this quantity, and of course, the number of AND gates is less than the size of C, therefore, the size of C is also at least this quantity, okay. So, this is actually saying a little bit more. So, what we have established is that the size is at least this quantity in one case. What is that case? When the approximator is identically 0. So, if the approximator is identically 0, then we get. Now, what happens if the approximator is not identically 0? So, these are the two cases that we will consider, and that would suffice. So, now let us move to the second part, that is, we want to establish a similar lower bound, but when the approximator is not identically 0. Wish I could have kept this written anyway. So, consider the two inequalities. So, each of the two inequalities let me state them. Now, we will look at it the other direction, that if approximate OR of G is less than f OR of G, and if approximate AND of G is less than f and of G fail for at most m square into L choose 2 by k minus 1 whole to the power p into k minus 1 negative test graphs. Okay. So here what we are saying is that both these inequalities or each of these two inequalities can fail for at most these many negative test graphs. So once again we need to consider both these equations. So here we are, and now we are looking at the inequality in the other way around. So when does this inequality fail? So note that an inequality will fail. So if, well, the first, both these inequalities will fail if f or of G or f and of G is strictly greater than the approximate version, right? So that is strictly less than the approximate version. I am just saying it the other way around. So f or of G is strictly less than this, which means that initially f and G did not have a clique, but the approximate, this process of constructing approximator introduced a clique, and the same thing for AND. Now, can a clique be introduced as a result of plucking? Absolutely, it can happen, right? I mean, there was a petal which did not have a clique, but the center has a clique. I am replacing the petals with the center, so that can happen. So plucking can introduce a clique over here. What about these operations? Okay, so of course, so here I am doing plucking. Here also the third step I am doing plucking. So plucking can introduce a clique. It can happen. So we will have to count this. What about these two operations? Replacing this with Cx union Y. Can this introduce a clique? So assume that both these two did not have a clique, but now this has a clique in a negative test graph. This cannot happen. So if these two did not have a clique, there is no way X union Y can have a clique, right? So that's a very obvious thing. So okay, the observations are plucking can introduce a clique in bracket, that is violate the inequalities. However, first step of F and G cannot change the, or does not violate the inequality. That's the more apt way to write it. What about the second step? If I am removing a set of size, some size, does that violate the inequality? Does it introduce a clique? Again, removing a set cannot introduce a clique. Right? I mean, it might remove a clique, but it certainly cannot introduce a new clique. Okay, so second step also does not violate the inequality. So what we see here is that for both these approximate or and, they can only be the inequalities can only be violated as a result of the plucking operation. That is the only thing. So we just have to count as a result of the plucking operations how many negative test graphs get violated. I mean, for how many negative test graphs these equations get violated. That is all that we have to count now. Clear?
How can in the first odd in the odd situation how can plucking introduce a
I mean, I can have a set, so I can always have a set A which does not have a clique, but a subset of A has a clique. Center is a subset. I mean, it can have a clique, right?
Does not have a click. It is not a click.
Which one?
I mean the petal itself
Is not a clique, correct? Yeah. Yeah, again, I shouldn't say does not. If the petal is not a clique, then it cannot.
I mean the petal is not a click, but
Its subset can be a clique. Can be a clique. Huh. Okay. So now we have to count. So what do we need to count here? So we have to count. So let me just state this. The probability. Okay. Let Z1 up to Z P be a sunflower with center Z. Okay. So what is that I am computing? When does the plucking operation introduce a clique? That is the probability that none, or what is the probability that that would happen? Let's compute that first. Probability that none of the Zi's have a clique, okay, but Z, or none of the Zi's, again I correcting ugly, is a clique, but Z is a clique. Okay, this is what I want to compute. Now, what is this equal to? So this I can write. So when is none of the Zi's is a clique? I can say this as this is OR of I going from 1 to P CZI and CZ. Right? So this OR is 0 if each and every CZI is 0, that is each and every ZI is not a clique, and this is 1. Now by conditional probability we can bound this by the probability that OR of CZI given CZ equal to 1, right, by conditional probability. Right. Now what can I say from this? So look at each of these events. Okay, so look at each of these events. Okay, so I have how many events are there? I going from 1 to P. So look at each of these events, CZ1 equal to 0 given CZ equal to 1. Okay. What can you say about all these events? Are they independent or not? Each of these events are mutually independent, right? Because the way I assign the colors, it is basically it's a random coloring. So the probability that, I mean, yeah. So each of these events are mutually independent by the way the coloring function was picked. So therefore, I can write.
Should use the fact that these form a sunflower so that no points are, like there is no common point among the different ZIs once we remove the center.
Yes. Yeah. Yeah, correct, yeah. So actually, yeah, so that is the thing. So each of these is I mean the fact that these ZIs form a sunflower means that if I remove the center, they do not have any common point, correct. Okay, so therefore now each of these ZIs is equal to 0. I can write it as product of I going from 1 to P, probability CZI is equal to 0 given CZ is equal to 1. Okay. Since the events are mutually independent, and this, so now observe these two events CZI equal to 0 and the event CZ equal to 1, these are negatively correlated. Okay, so basically if I have a, yeah, I mean the correlation between these two is negative. So therefore this is bounded by I going from 1 to P probability. So this is just simple working out. I mean if you have two events that are negatively correlated, it follows that this is the probability that CZ I can write it as this. Okay, and now what is the probability that a set Zi is equal to 0? So these Zi's are the petals. So what is the probability that it is 0? What does it mean to say it is 0? It means that this doesn't form a clique. This actually we proved. I mean we just computed this probability in the very first lemma. Okay, the probability is basically this. So L choose 2 divided by k minus 1. So it doesn't, the probability that it does not have a clique is the probability that there are two vertices which are colored the same, right. So we have seen this. So this is at most L choose 2 by k minus 1, right. And now I am taking this product p times. So this is whole to the power p, right. So this follows by negative correlation. Okay, so where are we? So we have shown, sorry, this was k minus 1 to the power n over here, yeah, missed this n in the lemma. So this is what we have as a result of one plucking. So now how many pluckings can there be? So again the total number of pluckings is at most m square. So therefore the probability that gate fails on some plucking is m square into this. And if I want to count the number of negative test graphs, it is basically the probability times the total number of negative test graphs, which is this, right. therefore number of negative tests that fail an inequality is at most m square. So this is the maximum number of pluckings times L choose 2 by k minus 1 to the power p. This is the probability that on a single plucking, what is the probability that it fails, and times the total number of negative test graphs, okay, number of negative tests. So this completes the proof of lemma 4. So now we will show a lemma that is equivalent to lemma 3. Okay. So what happens when the approximator is not identically 0?